All right, so the next chapter is all about radical reactions. We've seen radicals briefly, but not in very much detail. And radicals, does anybody have a way of describing them?
They make skin awesome.
They make skin awesome, so you can get radical damage from UV sunlight. That's one thing. But what is a radical? It's missing an electron. Yeah, it's an element that has an unpaired electron, and they tend to be quite reactive because electrons like to be paired. So let's compare this to a reaction we've seen. The first reaction we've seen is heterolytic cleavage. And with heterolytic cleavage, you have two atoms that are covalently bonded together. I'm just going to make them up as X and Y. And you can take the covalent bond and dump both electrons from that covalent bond onto one of these atoms, which means X in this case would be a positive charge, and Y, having two electrons, must be a negative charge. So you make cations and anions. All right. Conversely, we have something called homolytic cleavage. And with homolytic cleavage, you could have the same two atoms covalently bonded together, but in this reaction, one electron from the covalent bond will get dumped onto Y, and then the other one will get dumped onto X. So you'll have X with a dot, meaning one electron, and then you'll have Y with a dot, meaning it has one electron. These technically don't have charges, right? They are neutral compounds. However, because they have unpaired electrons, we know they're reactive, and we'll call both of these radicals. All right, if you notice, the arrows that I used were very specific for the situation. In the top one with heterolytic cleavage, we used a double-headed normal arrow, meaning that red arrow up here. However, in the lower one, I used a fishhook arrow, meaning it only had one side of the head. Anytime you see a single-headed arrow, that indicates that you have movement of one electron, not two electrons, as with a double-headed arrow. So let's make a note of that. So if you see an arrow that looks like that, that means that it's two electrons being moved, which is not the same, whoops, as seeing an arrow with a single head. That indicates that it's only one electron being moved. So you have to be very particular with drawing your arrows for these. Does that make sense? All right, so yeah.
So do radicals not have charges?
Radicals do not have a formal charge. Yeah, at least the way we have them shown here. Yep. So let's take an example of one of these. And we'll do homolytic cleavage. And in this example, I'm going to take the central carbon with 3 methyl groups on it and a halogen. I'm just going to call this X. And we're going to do a homolytic cleavage of that bond to the halogen. So one of the electrons from this covalent bond will get dumped over to X. The other electron will get dumped onto the carbon. And now if we think about this, we have a central carbon that has one electron on it. And then we have our halogen that fell off that has 7 electrons. Therefore, it wouldn't have a net charge, right? Halogens normally have a valence of 7. All right. My next question, though, is what is the hybridization of the central carbon? Not good. sp2.5. Close. So when we do Vesper theory, we look at the number of bonded atoms and the number of lone pairs. If you remember going back to Vesper theory, I was specific about saying lone pairs. I didn't say single electrons. Single electrons don't really take up that much space. So if we think about it, the hybridization, if we're ignoring that lone pair, would be sp2, which means it has a p orbital going on. So let's go ahead and draw that p orbital. p orbital is going to be going up and down like that. And the electron is going to be hanging out in the p orbital, and this carbon is going to be sp2, and then this is going to be a p lobe. My question for you is whether or not the electron's in the upper half of the p lobe or the bottom half of the p lobe. The answer is yes, right? If you remember, electrons don't behave like normal particles because they're super duper tiny. They're kind of wave-like. So in this case, it's a probability map. It's saying there's equal probability of that electron being in the top lobe of that p orbital as the bottom lobe. Electrons are weird that way. They don't follow the behavior of normal particles. They're much more wave-like than that. And if we think about this central carbon, the sp2 carbon, this must be trigonal planar. Oops. So it is kind of weird to think about that electron having equal probability of being on the top half as the bottom half. That gets into weird quantum chemistry that we're really not going to get into in this class. All right. The good thing with this is this looks a heck of a lot like carbocations, right? Carbocations are also sp2. The only difference with the carbocation is you don't have an electron in that p orbital. So therefore, the stability trends follow the same trends as with carbocations. So the stability of organic radicals follows the same trend as carbocations. What's the most stable carbocation you can have? The one that's stabilized with resonance, right? So if we think about it, we can say resonance is far away the best situation, followed by tertiary, followed by secondary, followed by primary, and last but not least, we've got methyl radicals. Methyl radicals are really, really unstable. You tend not to see them very often. All right? The tricky thing is, how do we show resonance with radicals? It's not super straightforward. So let's do radicals with resonance and practice our resonance arrow pushing. All right, so let's say we've got the following compound. I'm going to show all of our hydrogens here. We've got green hydrogens coming off the left. We've got a blue one in the middle, and we've got red ones on the right. So which of these do you think is most likely to be plucked off? The green, the blue, or the red? Does anybody have a guess? Think about if you were to remove a proton, which proton is going to be most acidic? Which one would give you something that's resonance stabilized? Everyone's saying different answers. So if we think about acid-base chemistry, if we were to remove one of those green protons, we would have a resonance stabilized anion. So the similar trend is true for radicals. So let's imagine what happens if we remove one of those green hydrogens. And so I'm going to show that by saying minus H dot, meaning we're going to lose one of those hydrogens and its electron. All right? So when that happens, we still have the blue proton in the center. We still have the two protons on the right. We still have these two green protons. But let's show our arrow. So for example, if we were to remove this proton, or sorry, not proton, hydrogen, we could show the homolytic cleavage where one electron goes to that hydrogen, and then the other one goes to the central carbon, which means we must have an unpaired electron right there. Make sense? All right, so now we've got to figure out how to show resonance with this unpaired electron. So this electron can hop around, and it can try to dump into this carbon-carbon bond. but it can't form a carbon-carbon double bond being only one electron, right? It needs to steal an electron from a neighbor. So for example, it could steal one of these pi bond electrons, and those two electrons together could form a new carbon-carbon bond on the left-hand side. However, we still have an unpaired electron from that pi bond, and that has to go somewhere. So we can shove it over to the right-hand side. So we still have the two green hydrogens on the left. We've got the blue hydrogen in the middle. We've got the red hydrogens over here. But now the radical electron is over on the right-hand carbon. So this would be an example of showing resonance arrow pushing. There's a lot more arrows than you typically see with normal arrow pushing because we need to show movement of each individual electron rather than pairs of electrons. Does that make sense? All right, I'll give you a practice one. All right, this practice one's going to be somewhat challenging. And the radical is on the upper carbon. So see if you can draw all of the different resonance structures for this organic radical. And I'll give you a hint that there's two other resonance structures. All right, let's try to do this as a group. So just like with any resonance in general, our goal is to delocalize things that are unstable, right? Whether or not that's an anionic position, a positive charge, or in this case, an unpaired electron. Okay, so we want to move this unpaired electron around. Are we going to move it this way? No. Nope. We're going to move it to the right-hand side, so I'll dump it down right there. It can go to an adjacent carbon-carbon bond, but not any further than that. All right, at that point, we haven't made a true pi bond because we need another electron, but that's okay. We can steal an electron from that pi bond, right? That means the other electron from that pi bond has to go somewhere, so we'll just dump it on that lower carbon. So now we've got a pi bond right here. We still have our other pi bond right there, but now we've got the unpaired electron down here. Does that make sense? Yeah.
Exactly why can't it go the other way? Like, is it just because of the adjacent orbital?
So the question was, why doesn't this electron go that way? We really couldn't find a way of forming a pi bond without violating an octet rule. That's one of the big reasons we don't want to draw a Texas carbon. Yeah, does that make sense? Yeah. Okay, so if we have this intermediate, or sorry, not intermediate, the second resonance structure, we can take this electron, we can dump it down, continuing going right, and just like before, we need to steal a pi bond electron, and then the other pi bond electron can get dumped onto the right-hand carbon. And so all three of these would be resonance structures, meaning that unpaired electron is residing across three different atoms at the same time. You can show a hybrid for this, but it gets super duper confusing with radicals to show where that unpaired electron is. So most of the time when you see these, you just see people draw out all three resonance structures. Yeah? That's a good question. For radicals, it gets a lot more complicated, so we're really not going to get into that. In this situation, we're going to assume they're all relatively equal stability. Yeah. All right. So let's take a look at the most common reactions that occur with radicals. And these are just kind of the elementary baby steps. The first one is radical cleavage. All right. And with radical cleavage, that's essentially the same thing as homolytic cleavage that we saw. So you can break covalent bonds using some amount of energy, and you can get two sets of radicals. In this case, an X radical and a Y radical. Like I said, you need some sort of energy in order for this to occur, which is a good thing, right? If you think about it, you don't want your bonds just breaking apart willy-nilly. You want them to stay together unless you're applying some sort of energy to break them. So the energy that we use can come in a wide variety of forms. It, however, is directly correlated to the strength of that bond. So the energy required is proportional to the strength of the bond. If it's a really strong bond, it takes a huge amount of energy to break it. So sometimes that comes in the form of high energy UV light or even gamma radiation. If it's a really, really weak bond, sometimes just a little bit of heat is enough to rip apart that bond. It just depends on the nature of that bond. All right, the other one is kind of the opposite of this. It's called radical coupling. And with radical coupling, that's where you have two radicals. And when they're close enough together in space, those two electrons can dump in and form a new covalent bond. And this occurs a lot in biology as well. It's what causes a lot of the oxidative damage. For example, when your skin's exposed to UV light, you'll actually make radicals in your DNA, and then your DNA can cross-link and form new covalent bonds, which causes a lot of problems, right? So radicals, being unstable, like to form new covalent bonds. All right, the next one is addition to pi bonds. So for example, if you've got a radical, in this case I'll just do X, and you've got some sort of pi bond, in this case I'll draw ethylene. This radical electron can reach out, and then one of the electrons from the pi bond will reach out and form a new covalent bond. But the electron that's left over must get dumped to the other side. So you'll get a carbon-carbon, let me make this a little bit clearer. You'll get a new carbon-carbon bond, and the carbon on the right-hand side, in this case, would have the radical. So that's another one. The other one, instead of addition, is elimination. It's basically the same thing, but in reverse. So if you've got this radical that we just formed, you could do the reverse reaction and say, well, maybe this electron that's unpaired dumps down, and then we break this covalent bond, form a new pi bond, and then eject off X as a radical. It's everything's the same, but just in the reverse order. Does that make sense? All right, and then the last one is a set of reactions with hydrogens. This is hydrogen abstraction. And with hydrogen abstraction, you could have some sort of reactive radical and some sort of alkane. So the R just means some sort of carbon placeholder, right? And this radical can actually steal a hydrogen. And when this happens, the carbon indicated by R is going to take the unpaired electron and will form a new bond between X and our hydrogen, and will make an organic radical. This becomes really important in synthetic chemistry. We are going to see a reaction where we'll do this as one of our first steps.
I have a question.
Yeah.
Do we draw the arrow from the bond or from the hydrogen?
Show it from the bond. So the question was, where do you show your arrow from? So for example, this arrowhead, try to show it coming from that covalent bond because it's stealing one of those covalent bonds electrons. All right, and then the next one is halogen abstraction. And this one's pretty popular with fire extinguishers. So some fire extinguishers are full of these special halogenated compounds. And what will happen is in a fire, you create a lot of radicals. This radical that's created in the fire will steal one of these halogens, basically quenching the fire. Does anybody know the problem with those fire extinguishers? They're super bad for the environment. In fact, a lot of the firefighting foams at airports use that sort of stuff. And they found that firefighters that deal with that foam have a ton of halogenated compounds in their blood, which is not a good thing. It bioaccumulates in the environment, destroys the ozone. It's just not good. We really try to only use these fire extinguishers under the most extreme circumstances where putting out the fire is of paramount importance. If you're interested, there's a section in the textbook that talks about it. I found it really fascinating. I had my PhD and I didn't know about all that stuff, so it's a good read. All right, so this works really well with just about any halogens. Usually you see that X2, meaning this guy right here, is either Br2 or Cl2. Does that make sense? So these are kind of the elementary arrow pushing steps for all radical chemistry. All right, let's jump into the most important reaction from this chapter. How do we halogenate alkanes using radical chemistry? Yeah.
So from all those radical things, how do you know which one? Like, are there any technically, or is it just you're given a radical and bromine?
So I'll show you the elementary reactions we need to know for this organic chemistry course. If you go on and take more organic chemistry, you can kind of jump down that rabbit hole. There's luckily only 3 reactions in this chapter, and I'll show you the reagents and the steps involved. Yeah. So before we start, let's do the following. So before we start, identify the hydrogen that is most likely to be abstracted. And I'll give you an example here. In fact, sorry, I'm gonna just, it's gonna bug me. There we go. So we've got this compound with a bunch of hydrogens on it. Our goal is to find the hydrogen that is most likely to be abstracted. Which one do you think will give you the most stable radical in the end? The one coming off the central carbon? Why is that? Yeah, it's a tertiary carbon. So just like forming the most stable carbocation, we want to form the most stable radical, which would be coming off the most substituted carbon. So for example, this results, or let me rephrase this, abstraction of this proton, or hydrogen, holy cow, can't say that. Results in a tertiary radical. If we were to abstract one of these protons coming off of one of the methyl groups, we'd have a primary radical. Those are a lot less stable, right? So that's the first thing I always do when I'm looking at a radical reaction is I identify the hydrogen that's most likely to be abstracted. So for example, we could show this reaction arrow and we could say, when this reaction occurs, it's very likely that we're going to end up with this radical, which is tertiary, plus our hydrogen radical. All right, now we can start doing the overall mechanism now that we've identified the hydrogen that's going to be most reactive. All right, so step 1 is initiation. And for radical halogenation, initiation is an important step. Initiation usually involves elemental bromine, and we'll talk about why a little bit later. And our goal is to break this bromine-bromine bond and initiate formation of our radicals. And just like I said before, you need to apply some sort of energy to the system in order to break that covalent bond. This energy can come from either heat or UV light, which is represented by the symbol for Planck's constant and frequency. And if you do that, you can generate 2 bromine radicals. The bond between 2 bromine atoms is relatively weak in the grand scheme of things. All right, step 2, after we've generated our radicals, is propagation. Let me make a note here. Initiation means to create a radical. What do you think happens in propagation? Yeah, the radical is not created or destroyed. All right, so let's take a look at what happens once we have our bromine radical. Got this bromine radical. We've got our starting compound. Which we said looks like this. We said that this hydrogen coming off that central carbon is most likely to be abstracted. So now we can show the hydrogen abstraction, where we're going to rip off one of the electrons from that covalent bond. The other electron will go to that central atom. And so now we've created a new covalent bond between bromine and that hydrogen. We have a radical on the central carbon. Let me slide this over. However, if you go back up and you look at my definition of propagation, it says that the radical that we just created in step 1 reacts, but it shouldn't be destroyed. However, I don't have a bromine radical anymore. That means we need to regenerate it somehow. So in the next step, you still have some bromine around from step 1 that wasn't cleaved, meaning it didn't undergo complete homolytic cleavage. Whenever you do this initiation step, chances are a small percentage of that bromine will cleave into radicals, but not all of it will be. So we will still have some additional bromine around. So in this next step, this radical will reach out and do a halogen abstraction. We'll form a new covalent bond to our bromine. Let me slide this over. And we regenerated our radical. So that's an important step of propagation. This is really important because once you regenerate the radical, that bromine radical, it can find more of your organic starting material and continue this loop over and over and over again. That's why it's called propagation. Yep.
So you showed the 2 red arrows of the bromine and that radical attached to that central carbon coming together. They're not coming together in a separate instance. It's actually just a bromine binding to the central carbon.
So are you talking about this step right here?
Yes, sir.
Okay, yeah, so the radical off of the carbon, right, is going to steal one of the electrons from the bromine-bromine bond and form a new covalent bond to that bromine. However, the other bromine is going to kind of be kicked off and only have 1 electron instead of 2. So that's the radical being regenerated. And then that regenerated radical can go find additional unreacted organic starting material and continue this cycle over and over and over again. Yep.
In real life, what happens to the radicals is we don't have like just a bunch of radicals freely floating around all the time.
Yeah, that's a good point. So maybe it's a tiny percentage of your solution that's bromine radicals. But if you're constantly regenerating it, it doesn't get used up. However, your organic starting material eventually will get exhausted. So what I mean by that is this organic starting material, after a while, will eventually get all used up, and you will have created nothing but this in solution. So then the question is, well, what happens after the propagation's used up all of the organic starting material? That leads us to our next step, which is called termination. So termination is where you eliminate your radical. This typically occurs at the very end of the reaction when there's no more chemistry you can do for your propagation step. So let's take a look at different ways we can accomplish termination. There's actually 3 options. It's not that one's right, it's that any of these 3 options can occur. So one option could be maybe you've got your bromine radical floating around and it finds another bromine radical in solution. These two could couple together and regenerate your new bromine-bromine bond. So that's nice and easy to show. We started out with radicals and we've ended up with a product that doesn't have any radicals. Another option would be maybe we still have some of our organic radical around. And we've got a bromine radical. If this bumps into that, we can form a new covalent bond and make more of our halogenated organic product, which is kind of nice. That was the organic product we made in our propagation step. So that's also an option. The last option is arguably the worst option, but somewhat unavoidable. And that's where your organic radical finds another organic radical. And when this happens, you can actually form a new carbon-carbon double bond. This usually isn't as likely. Does anybody know why? Sterics, right? Sterically, this is a lot less likely to occur than the top 2. But if you were to look at your reaction mixture, there's a fair chance that you would observe this as one of your minor products from this reaction mixture, where you'd create a new carbon-carbon bond. So however you want to show your termination step is completely up to you. I'll give you one guess as to what students usually choose. Which one? The top one. It's like it's way easier. Yeah.
So I'm curious, with the BR-BR connecting, would that happen more often than the second one, or are they both equal?
That's a good question. I would say the top one's probably the most likely one in solution. If we look at our initiation step, we created those 2 radicals. There's a fair chance those radicals can recombine before they have a chance to find an organic starting material to do the first step of our propagation. So I'd say the first step's fairly likely. Yep. You may see either or in your textbook, depending on which textbook you're looking at. More often than not with halogenation, you'll see UV light rather than heat. So I would say that this option is more likely. Usually you see heat with peroxides, not with halogens. But it's one of those things where I don't want to cast too wide of a net, but I want to show you both possible options. Yeah. All right. Let's make a note, too. And the note is, if you have excess Br2, then the next most reactive hydrogen could be halogenated. However, we saw that the other remaining hydrogens on our organic starting material were coming off of primary carbons, It's not super likely that it would occur unless you were to aggressively push this reaction by flooding it with an enormous excess of bromine. Does that make sense? But let's say you had 2 tertiary positions and you added excess bromine. It could be very likely that you would halogenate both of those tertiary positions and get your dihalogenated product. I will show you another example, though. So this is note number 2. This reaction will work with Cl2, but it is messy. And I'll show you what I mean by note number 2 here. So if you take something like methane and you react it with chlorine gas and you react it with UV light, you can add in 1 chlorine, you can add in 2 chlorines, you can add in 3 chlorines, or you can add in 4 chlorines. This reaction is super hard to control. So let me make a note here. The radical reaction is hard to control. So oftentimes when you try to do radical reactions with this, you get this horrendous mixture of products that you have to isolate, meaning you have to purify through distillation, chromatography, something like that. It's pretty hard. All right, so going off of this, I wanted to talk a little bit about regiochemistry. All right, and what I mean by regiochemistry is the position in which the halogen's installed. So which carbon does it get installed onto? So for example, this organic starting material that we saw in our example, we said if you react this with Br2 and UV light, that we will observe the bromine getting attached to the central carbon. And when you look at this, it's going to be pretty dang close to 100% of our product. We might observe some of that organic product where the 2 organic radicals coupled together, but for the most part, we're going to make almost 100% of our desired product. If you do the same reaction with elemental chlorine and UV light, you could get chlorine added to that central carbon, or you could get chlorine added to one of the primary carbons. The reality is chlorine is very promiscuous. You'll get about 28% of the product shown on the right and about 72% of the product shown here. So chlorine is not very regioselective. That means from a synthetic point of view, it's not super practical. Does anybody know the other challenge of doing this reaction? Chlorine's a gas. It's a lot harder to work with a gas than it is a liquid, which bromine is. So the top reaction's far and away more common than working with a poisonous gas like chlorine. All right, that normally leads to somebody asking me about the other halogens. Nobody asked me today. Does anybody know what happens if you deal with fluorine, F2, which is also a gas? It's super not selective. In fact, it's pretty dangerous to do. If you do radical fluorination, there's a fair chance it will blow up in your face. I remember hearing about a chemistry talk where the guy came in talking about some of the new radical fluorination techniques, and he said, I'll give you 3 reasons never to do radical fluorination, and he held up his remaining 3 fingers. So it's very, very exothermic to the point where it will cleave carbon-carbon bonds. It's not regioselective. It will over-fluorinate. It's a tough reaction to do. They do it in some industrial settings, but it's not very common just because it's just very challenging to control. What's that? I don't know, actually. I don't know if anybody would do that. Maybe. Did you have a question? Yeah, so really we don't see radical fluorination synthetically because it's too hard to carry out. That being said, there's more modern organic chemistry where they're trying to fluorinate organic compounds for new drugs, and they do other techniques that are a lot more safe to accomplish. Yep.
I have the same question about chlorine. Why would you use chlorine if it constantly gives you, and it's just hard to work with?
It's synthetically, sometimes you need to get a chlorine on there, and so you're like, well, I'm going to take a hit. This is the best way I know how. The reality is for most synthesis problems, you'll see reactions with bromine. All right, one last note before we leave. All right. Let's say I do this reaction with bromine and UV light. We know that the tertiary carbon, meaning the hydrogen coming off right here, is likely to be abstracted and replaced with a bromine atom. Are we going to get one product or more than one product? More than one? Why? Let's think about it, right? That bromine really doesn't have a strong preference about adding into the top face of the radical or the bottom face. We saw that it's going through an sp2 intermediate that's trigonal planar. So the bromine has really no preference. So what would these two be related as? Enantiomers. So that's one unfortunate thing with a lot of the radical chemistry that we'll see is it's not stereoselective. It'll give you a mixture of different stereoisomers. So you do have to watch out for that if you're creating a new stereocenter. Does that make sense? Yeah.
Why not iodine?
Why not iodine? That's a good question. I think carbon-iodine bonds tend to be rather weak, and so I think it leads to a lot of problems because of that. You normally just see reactions with bromine. Yep. All right, that's where we're going to stop today. Tomorrow we'll come back in and we'll talk about other halogenation reactions.